Morning everybody. Today we will discuss the Young's modulus and we will discuss behavior of different material. We will discuss the elasticity and elastic behavior. This is a typical Young's modulus graph and you can see a lot of materials behave in a different way. Okay, how do we find Young's modulus? Learning objectives. First of all, we need to understand the keywords that are associated with the deformation of different types of solids. We will be able to calculate stress, strain, and therefore we can find the Young's modulus. And we will be able to describe different material in a graph and how the different material behave. First thing, what do we mean by elasticity? That is the ability of a solid to regain its shape after it has been deformed or distorted. Okay? But which law would follow this? Think about this. Tensile. Tensile is a deformation due to the stretching. Tensile is like stretching. Compressive deformations, like pushing, is a deformation due to depression. And then we have ductility. That is the ability to draw a material into a wire, and especially metals are very ductile. And brittle is a material that breaks without any give. That means it just suddenly breaks, yeah? So it cannot be stretched permanently. Now, what is the tensile stress? Well, it's just the same as pressure, but now when we are stretching. So it is the force per unit area of the cross section when a material is stretched. Yeah. So when we have a wire of length L and cross section A, then the tensile stress is the tension divided by the area, and this tension is nothing more than just a force. So the tensile stress is in units Newton per square meter, or we can express it in pascals. Yeah. Don't forget how we find the cross-sectional area of a wire. Yeah. Depending if we use the radius or if we use the diameter. Okay. Then we have the tensile strain. It's actually something similar that we use in the Hooke's law. It is the ratio of the change delta L to its original length. We can say L0 or L, yeah. So when we have a wire of a length L, original length, then the tensile strain is the extension divided by its original length. And we use an epsilon for this. So delta L over L. What's the unit? None. Yeah, it's only a number, it's a ratio. Okay. Now, many companies, they want to know how different materials are behaving when you put them under stress. How they behave? Are they stiff? Can they be elastic when they go back to their original length? Now, let's look at the stress strain curve. Just an introduction. On the left side we have the stress, and on the horizontal we have the strain. And we see this curve. How does it look? Well, we get first a straight line. That means, what do you think it follows? Indeed, Hooke's law. And then it's going to behave in a different way. And we will see actually that, for example, this metal rod is going to neck. We will talk about that. Okay. So let's look at the graph a little bit more into deep. We have different regions, and it's very easy to use the Young's modulus because then we can compare materials easy with each other. Okay. Okay. First region is a straight line, which means we have Hooke's law. So when we go from 1 to 2, we put a stress on it, and let's say we release the stress, no more stress, then the wire or the material goes back to its original state. At 2, we have reached the limit of proportionality. That means after that, it's not going to obey Hooke's law anymore and slowly goes to deform. Then we have the elastic method, and this is the point where the material is stopping to return to its original length when we reduce the stress. Okay, we move on to number 4, and this is actually almost the maximum force, but at this point we will see that the material is going to neck. Okay, and at number 5, that is where we find the maximum stress that we can apply to the material after it has been deformed, and we call this the ultimate tensile stress. And at B we get our breaking point. Even though a material can be very elastic, but it's going to neck, and in a certain moment it will break. Okay, let's again discuss some definitions. The elastic limit, that is the maximum amount of material can be stretched by a force and still return to its original shape and size, and that means the material has no permanent damage or change in shape. Then we have the yield point. This is the point beyond the elastic limit, and this point is reached at which there is a noticeably large permanent change, and this results in plastic behavior. And then we have the UTS, the optimal strength, and the maximum stress that can be applied without breaking. Okay. Plasticity means it doesn't return to its original size and shape when a force is removed. The stiffness, we discussed it a little bit already with Hooke's law, with the springs. This is actually how difficult can you change the size or the shape of a material. For example, steel wire is stiffer than thin steel wire. Means it is still the same material, but the thicker the steel, the stiffer it is. Obviously, short steel wire is stiffer than long steel wire when we use the same diameter. And of course we have a difference in material. Steel, for example, is much more stiffer than copper, same diameter and length, because if we compare all these, copper in this case is less stiff, so it extends more per unit force. Okay, let's look at our Young's modulus. We know now the stress, the tensile stress, and we know the tensile strain. As said, in region 1, Hooke's law is obeyed, and is of interest. Why is of interest? Because we can use it for finding the Young's modulus. Now, the Young's modulus is defined as tensile stress divided by the tensile strain. So we can find it from the gradient from the graph. So Young's modulus, big E, is sigma over epsilon, is Stress is force over area divided by strain delta L over the original L, and we have then the unit as delta L over L has no unit, then the tensile, the units come simply from the tensile stress, so that is in Newton per square meter or in Pascal. Okay. We can rearrange this formula. It doesn't matter so much. Okay. So, but if we want to know the Young's modulus, we can use the gradient of the Hooke's law graph. Okay. Nothing special about this. Okay. Okay, let us look a little bit at different material, and we are going to compare brittle material with ductile. What do we see? In brittle material, it's following Hooke's law, at a certain moment it's not going to deform, and it suddenly breaks off and it finds its UTS. When we look at the right figure, this material is ductile, and you'll see that it is going to deform in a way normal plastic material or plasticity behavioral material is going to change when stress is applied over a certain area. So in this case we compare the stress strain graphs of brittle and ductile material, for example glass and copper. Let's look at some more graphs. We have steel, glass and copper. Now what can we say about this graph? Which of the materials is the most stiff? That is the steel, because it has a higher Young's modulus. Does it behave like ductile? Yes, it's going to deform. Okay, so the strongest material is also steel. When we look at glass, slightly lower Young's modulus than steel, but we see it deforms a little bit and then it breaks off. If we look at copper, it follows nicely a long stretch of the Hooke's law. We see that it's way less stiff and it shows plastic behavior, which will break at the end. Okay. In our next slides we will be looking at what is going to happen with the material when we load, put its stress on it, and when we unload. Loading and unloading. And what are our objectives for loading and unloading? Learning objectives. We have to understand that once the elastic limit has been exceeded, the force extension graphs for loading and unloading are not equal anymore. That means, for example, if a material follows Hooke's law and we put a stress on a material, and within the region of the Hooke's law we just unload the stress, to say so there's no more force, the material is going exactly back at its own material. So the graph goes back in a straight line. However, if we have exceeded the elastic limit, that means the material is going to deform. The graph is not going back the same way anymore. Okay, now this graph or these curves, we call them the hysteresis curves. Yeah, and with these hysteresis curves we can be able to define the different materials, how they behave, but also the energy changes that are taking place when we load and then unload. Going back to some definitions that we have described, because we're going to use them in this again. Ductile materials have a large plastic region just before it fails, and the material is going to neck. That means that the cross-sectional area is going to decrease. Okay. If we get necking, there's an increase, of course, in the tensile stress, force over area. Materials that show little plastic behavior and there is a sudden failure, we call them brittle. Okay. Loading and unloading. So, when we have a material that is in the region of the Hooke's law, again it follows nicely back and the load and unloading will be exactly the same. Yeah? This is of course not true anymore if the material behaves like plastic or ductile. It's going to deform. Again, how can we find these curves and how do we have to describe them? Let's have a look at the metal wire. We're going to increase the force on the metal wire. It follows nicely the Hooke's law. At a certain moment it has reached in elastic limit and is going to make a curve. Okay, now these curves, what is going to happen when we reached a certain moment that the material has been deformed? It goes in a line down back, which means there is a difference in energy. And if we unload, you will see that the unload curve is parallel to the gradient of the Hooke's law. And when we see, when it goes back, it means that the original length has been stretched. That means the original length has become larger. What you saw, what we just says here, we see that with the metal, it nicely goes back according to the Hooke's law. Yeah, so same gradient. However, when we look at rubber, it completely behaves in a different way. Rubber is really a material that can stretch easily, yeah, and we have tried it in the class and we have seen how much rubber can stretch. Yeah, there is a very low limit of proportionality, that means following the Hooke's law, because it's going to stretch already. Yeah, so in contrast, elastic materials such as rubber loads and unloads in a completely different way as, for example, metals. Yeah, and the graph is more like curled and then uncurling. Yeah, you need to represent these graphs and understand what is happening here. Okay, another material, polyethylene, or let's say simple plastic bags. There is definitely a plastic deformation with polyethylene or simple plastics, and we get a permanent extension. Yeah, this is because the weak intermolecular crosslinks exist between the molecules. These break during stretching and new bonds reform when the tension is removed. Yeah, so for each material you see there are different types of curves, yeah, and distinguish the different curves of steel, rubber and plastic with each other and how they behave. Okay, now we're going to the next part, and is how do we find the strain energy. All right, how do we find the strain energy? Okay, we already looked in the Hooke's law how we find actually the energy that we put in a spring. Now remember, work done by an object is force times distance. Okay, so we have been using the area under the force extension graph, which is actually the work done to stretch the material. And we call this actually simply the strain energy. Now, when the graph is linear, the work done during the stretching is recovered when it's unloaded. So, what we mean by this is, we put energy into a material, the material is going to extend or to stretch, yeah, and when we unload, all that energy comes back in it. So that means when we have the straight line following Hooke's law, it follows exactly back the Hooke's law, yeah. However, in our example of rubber, what do we see? We see regions A and we see B. Now, if we follow the graph, the blue line is the energy we put in the system. So the area under A is the area of the energy we put in. Now, in rubber, the curve is going to follow a completely different curve. Yeah. Now, when it goes back, that region B is the work done by the rubber returning to its original. So, how do we find the loss of energy? That is the blue line minus the red line, and what I mean is the area under the blue line minus the area under the red line, and that is region A. And this can be energy loss in heat. Well, if you are going to stretch a rubber band and you do it a little bit fast, up and down, you will see that the rubber band actually is going to get warm. Okay, this is the end of this slideshow. Probably tomorrow we'll start with waves and I will load it up. If you have any questions, please let me know, okay?